Mic check 1 2. Mic check 1 2. Okay, so today I'm going to go through an overview of the standard setting method that we're going to be using in our standard setting meeting coming up on June 30th. So I'm going to introduce a few terms that will be important to know, and I'm going to walk us through the method that we're going to use to come up with the standard of performance. And to do that, I'm also going to show some software that I've written that will aid us, hopefully, in doing these activities. So why don't I start things off by just introducing some terms. So there's going to be a few terms that we are going to have to get to know pretty well in order to do this work. And the first big one that we want to be able to know is, let me share my screen here and I'll annotate while I talk. Let's share screen. So the first big term that we really need to make sure we know is minimally sufficient. Let's make this big. Zoom. Minimally sufficient implementer. And the minimally sufficient implementer, what we mean by this is an implementer who's doing just enough to pass the test. And this minimally sufficient implementer is sort of the target we're looking at. So let's get a little more into that. So I stop sharing my screen here for just 1 second. So we have these performance level descriptors, which the text of which has been sent in the same packet that you received the link to this video for. So you may have already seen these, but I'm going to go ahead and pull them up now because they will be helpful as we talk about this thing. So our performance level descriptors were written by many of the individuals who are on this call. So they won't be new to most of you, but they may be new to some. And what these performance level descriptors are a description of what someone, they're a description of an implementer who is implementing the SDLMI with minimally sufficient fidelity. So that is to say that if we look at one of these performance level descriptors, we can go ahead and grab adherence here. This accurately describes any implementer's implementation that is minimally sufficient in terms of alignment with the SDLMI as intended. So this description, I'll go ahead and read it aloud, is adherence is defined by A, teachers delivering SDLMI instruction consistent with their individualized SDLMI implementation schedule, and B, teachers during instructional sessions addressing the 3 SDLMI core components namely presenting the SDLMI student question that is the focus of the lesson, meeting the aligned teacher objectives, and using aligned educational supports during instruction based on student support needs. The performance level descriptor here, as was intended, helps paint the picture of what a person who is above the minimal passing score on the adherence component of the fidelity measure, what they are to look like, how we might describe them. Now, when the people who helped write these performance level descriptors came up with them, they were imagining the minimally sufficient implementer. And again, we just covered what the minimally sufficient implementer is. That's the implementer who's doing just enough to pass the measure. So, it's not the most stellar implementer in the world, but it's also not, an implementer who's not doing enough, right? It's an implementer who's doing just enough of a good enough job of aligning with how the SDLMI is supposed to be done, that we say, yeah, they're minimally proficiently implementing the SDLMI. So with these performance level descriptors as the target for what we're looking at, your job is to look at these descriptors and imagine in your mind an implementer who just barely meets this description, right? Not someone who meets this description and a whole bunch of other things, and not someone who meets this description, to the maximum possible extent, but someone who, just barely ekes out, an implementation that meets this description. That is what the minimally proficient implementer is. So keep that person in your imagination, while we're talking about these standard setting activities now, and certainly when we come on June 30th to actually do the standard setting. It's really important that you imagine this minimally proficient implementer. Please don't, let your imagination wander to other implementers that you've worked with, or implementers you may be about to work with in the coming year. Try and focus on that minimally proficient implementer, because that minimally proficient implementer is the person who best characterizes where the cut score of this test needs to go, right? So the cut score is the point. I'll go ahead and actually create a visual aid for this. Let's see. Share screen. So when I say the cut score, what I mean is that, pretend or imagine that we have some test, and that test has a distribution of scores. Let's assume that they look approximately normal. So, here on the y-axis, I have my number of examinees who take the test. And this test, of course, could be our fidelity assessment. And along the x-axis, I have the total score on the exam. And let's just pretend for ease of explication that this exam has a total score from 0 to 10, right? So the worst score that someone can get is a 0, and the maximum possible score is a 10. So, this test, it looks like, has just about, a more or less perfect normal distribution where, most examinees are scoring near the middle, and some are scoring to the extreme, and some are scoring to the other extreme. Now, when I say a cut score, what I mean is that, there's some point on this total score where we say anyone above that point passes and anyone below that point fails or does not pass. So this point could be anywhere, and the the meaningfulness of where the location is chosen for the cut score should be defensible. And that's, of course, what we're trying to do. What we're trying to do in our standard setting activity is to choose a point for this cut score that is defensible. And the way we're going to do that is by looking at each item under each of our 3 different domains and uh, sort of choosing ratings for those items of how likely we think the minimally proficient implementer would score on them. Now, I'll get into that in more detail in just a moment, but to finish up the introduction to what I mean by a cut score, suppose we have some exam that scored from 0 to 5 on the total score metric, and we choose some point, and I'll go ahead and just draw it here. Let's say we choose some point, let's say where the 6 is, and we say that this is my cut score. So what that means is that anyone above that cut score passes, and anyone below that cut score fails or does not pass. So there's a couple of really important things to talk about here. That, when we choose this cut score, no matter where we put it, there's going to be people just due to random error who might not pass when they should have. And there are going to be other people who do pass when they shouldn't have. For me, it's always easiest to talk about these things when I'm talking about some type of licensure testing, which isn't too far of an analogy from what we're talking about with the STLMI fidelity measure. But for a while, I worked with people on the United States medical licensing exam. So, on that exam, you can imagine that there's some people who, and maybe I'll go ahead and do a new page for this, since I've sort of maxed out what I can fit on here. Let's go to, oh, how do I go to a new page? I thought that would be easier than it is, but why don't we just go out and I'll start a new notepad. I'm positive that I can do that. Probably just needed to scroll down or something, but whatever. So, let's go back to this, and I'll leave some of the text out just to make it easier. But let's say that this is our cut score of 6, right? There's going to be some people who score a 7 at a particular point of examination. So say we examine on, let's say we examine them on June 1st. And it still hasn't updated, which is troubling. There we go. And then let's say that we give them another examination. We'll go ahead and create a table for them. Let's say that we, examine them on June 1st. Say these are dates and these are scores. Say we, give them an exam, every day of the week for 5 days. Let's say that they get a 7, they get a 5, they get a 5, they get a 6, and they get a 7. So this person's average score is, did I do this right? Yeah, I did. This person's average score is below a 6, right? It's just barely below. Ooh, no, it's exactly 6. Let's do one more. Let's say that we give them one more exam and they get a 5. So this person's average score is below a 6. We can calculate it if we want to, right? So their average score is 5.83. So their average score is about here. It's like a 5.8. And they have like a distribution around that score, right? Where we expect them to score. Um, and ooh, I didn't draw that very well in the middle. Let's try that again. Come on, Jesse. There we go. That's about what I want to draw. So this person, suppose that what we just have here, this set of 6 test points, suppose that that's a good representation of their testing. For any examination, there's going to be some amount of random error in their scores. These are just things that happen by chance. Like maybe we observed them on a bad day, or maybe we observed them on a good day. Maybe they didn't drink their coffee in the morning. Maybe they drank too much coffee in the morning, right? These are just, the infinite, what Shakespeare might call the slings and arrows of outrageous fortune, right? The things that nobody can control. Now, somewhere in that conglomeration of their test scores, somewhere in the middle of the conglomeration of this hypothetically infinite testing, we find their true score. But there's going to be this distribution around that at which we observe all these other things. So what that means is that there's a chance that this person whose true score is a 5.8, there's a chance that we might give them an exam and they might score a 6 or higher. And that means that we might give them a pass when they don't actually have the requisite skill or knowledge to be deemed, proficient at whatever this exam is supposed to be measuring. So when we do that, when we pass an examinee who shouldn't have passed, we call that a false positive, right? And what that means is that that's an examinee who should not be passing, right? Who should not be deemed quote unquote positive above the cut score, but whom we have falsely attributed to be so. And it's not too big of a jump to imagine the opposite happening, right? We could imagine some examinee who has, and I'll go ahead and erase this other one that we had right here. Let's imagine some other examinee who's maybe their average is like a 6.1 and they have some distribution around that 6.1 in which it's possible that we observe them on a bad day and we think that their score is here, it's maybe like a 5.8 or something. And but if we observe them, multiple more times, we would learn that they were supposed to have passed. Point being that this person, who we may arbitrarily fail, is a false negative, right? They are a false negative, right? Someone who should not have failed and yet did. So I think I can stop sharing this tablet screen now. So I'll go ahead and type these out really quick and share my screen again. So false positive, an examinee who should not have passed the exam and yet received a passing score, and a false negative, an examinee who should have passed the exam and yet received a failing score. So these are some important terms to keep in mind. Just generally speaking, as you decrease one of your chances of these errors, you increase your chance of the other. I guess what I'm trying to decide if I want to share my other screen again. I guess I'll go ahead. Share screen. So if we moved this cut score that we have here, if we moved it up, I'll go ahead and make another page for this. So if instead of a 6, we decided to move our cut score up here to a 7. Ooh, that's a squiggly line. If we decided to move it up to a 7, well, what's going to happen? You know, again, we had that examinee who was like a 5.8 for their average, and we had some other examinee who was like a 6.1. Well, now my line's in the wrong spot. Let's try that one more time. $6.1. And what's going to happen as we move the cut score more to the right is that we're going to have fewer and fewer false positives because we're going to make the exam really, really hard to pass. And what that means is that pretty much the only people who are going to pass the exam are people who, should be passing the exam. But what that's going to do is it's going to make it more and more likely that we fail examinees that should have passed, right? Again, because the exam is very, very hard. And the sort of pros and cons of whether you want to, reduce the amount of false positives, and probably increase the rate of false negatives, or vice versa, sort of, has to do with the implications of the exam. So in a licensure exam, like medical licensing, it's generally understood that false positives are more dangerous than false negatives, right? Giving a person a medical license, giving a medical license to a person who isn't competent to practice medicine is generally deemed as more of a risk than failing a candidate who should have passed, because passing that unqualified examinee, they're potentially going to go out into the world and do harm to many people, whereas failing someone who should have passed will certainly be harmful for that person, but weighing all of the harms, it's generally accepted that it's the lesser of the two possible harms. So the way in which we might weigh false positives and false negatives for the fidelity, the SDLMI fidelity measure, is something that we can talk about. But all things being equal, that we neither want to fail implementers who should be passing, nor pass implementers who should be failing. If we treat those two things as equal, right? Then our conception of the errors don't really need to be differentiated between false positives or false negatives. We can sort of think of the total error, right? That all mistakes are equal. We can talk more about this when we have our meeting on June 30th. So now that we have covered, I'll go back to sharing my my other screen real quick. Share screen. Now that we've covered what the minimally sufficient implementer is, we also covered what a cut score is, the exam score at which point and above an examinee is deemed to have passed. And we've also covered false negative and false positive. Now that we've done that, we're going to talk about the Angoff method of standard setting. So again, our goal here is to come up with a cut score. We're actually going to come up with 3 cut scores because we need one for adherence, we need one for quality, and we need one for responsiveness. So we're going to come up with cut scores for each of these that are defensible. And there are lots of different ways to get there. But the way that we're going to be using is called the Angoff method, sometimes called the modified Angoff. And what this method does and is it's very systematic. We're going to look at each item on the measure. I have all of the items here. We're going to look at each item on the measure within a given domain, and I'm going to have you, the experts, come up with estimates for each of those items on how likely the minimally proficient implementer would be to get a certain score. So what do I mean by that? Well, let's take this, and I'll go ahead and pull up the actual measure because it's probably easier and more familiar to people if I do that. So blow this up. So I won't use part B since that's what we're actually going to be working on together, because I don't want to put any kind of preconceptions in anyone's mind. So I'll go ahead and pull up part C. Again, we're going to be focusing on part B for the actual standard setting, but let's look at part C. So part C, this first question, let's just think about it abstractly as just a test item that may be influenced by the same constructs that we've been talking about for part B. So this item is rated on a 5-point scale, and the minimally proficient examinee, they probably have some probability of getting a 1 on this item. They have some probability of getting a 2. They have some probability of getting a 3, and they have some probability of getting a 4, and they have some probability of getting a 5. And what I mean by that is if you took 100, more or less interchangeable, minimally proficient implementers, and you observed them, there's going to be, some number of them who get 1s. There's going to be some number of them who get 2s. There's going to be some number of them who get 3s. There's going to be some number of them who get 4s, and there's going to be some number of them who get 5s, right? Just heard a sound on one of my devices. Hopefully it's ignorable. So the quantification of those numbers gets after the probabilities of these things. So what I'm saying right now might sound very abstract, but let me show you what this looks like. I've got an app to help us think about this. So so when we actually sit down and do our standard setting, we're going to use this app. that I've built. Basically, the way that this app works is you'll be assigning the minimally proficient implementers to the different scores. So for this item, just happened to grab this one. Did the students demonstrate knowledge of their goals and/or the process to achieve them? The possible answers to this are not at all, a little, or somewhat. So, say that we have 100 of these minimally proficient implementers. Well, some number of them are going to get ones. Maybe we think that a minimally proficient implementer is going to get a 1 60-ish% of the time, right? Another way to think about that is that of my 100 minimally proficient implementers, 60 of them are going to get a 1. Okay. And then let's say that maybe, 20 of them get 2s and maybe 20 of them get 3s. So you can see up here, the current expected value for this item is a 1.6, right? It's still closer to 1 than it is to 3, but because there's some weight now given to 2s and 3s, the expected value, is about a 1.6. So what this means is that if I took 100 minimally proficient implementers and I gave them all this item, the sort of average response across those 100 implementers would be a 1.6. Now, why this matters is that, again, what we're trying to get after is the total score that we think that we want to argue is the point where anyone above that is, minimally proficient, and anyone below that isn't. And so if we look at each item within a domain, and I'll pull those up again. If we look at each item within a domain and we come up with the expected score that we think a minimally proficient implementer should get for that item, and we do it for all of the items, then the average of those expected scores for the minimally proficient implementers is going to be our cut score. So let me give an example of this. Let's say that we take 3 items. This is for a hypothetical domain. Could be one of the domains we're talking about, might not be. Let's say that we just have one judge. So let's just think about yourself and say you're the only judge who's determining the cut score on this. Let's say that on the very first item, you said that you were thinking about the minimally proficient implementers, like this. Let's say that this is our hypothetical item, and let's say that you said that there is that 32 of those minimally proficient implementers would score a 1, and that 40 of them would score a 2, and that 28 of them would score a 3, right? So the current expected value is 1.96, right? Let's write that down, 1.96. And let's say that you then went on to the next item, right? So let's say that we went on to some other item. Let's suppose that this is a 3-item domain, similar to the this is the adherence domain. I don't know why I don't have it written here, but let's say that it's the adherence domain. And let's say on the next item, you think that, go ahead and set these back to 0. You think that 45 of the minimally proficient implementers would get a 1. Let's say that you think that 30 of them would get a 2. And let's say that you think that the remaining 25 would get a 3. Now our expected value is a 1.8 for that item, right? We think that the expected value across 100 minimally proficient implementers is a 1.8, right? That's sort of what the average score for them would be. And then let's say that we have one more item, and let's say that, we sort of get a wash on this one. Let's say that like all the responses are more or less equally likely, so that we get like 33, 33, and 34. So the expected value is, pretty much right in the middle, a 2.01. So 2.01. Well, what that means is that the average of these three things, which is a 1.923 here, 1.923. This, for the judge who came up with these ratings, this is the cut score. This is where we can argue, a minimally proficient implementer would score, because we now know what we would expect them to get on every item. And, by summing those items, by taking, oh, and sorry, losing my mind here. What I should be doing is summing. So this is the sum score that the minimally proficient implementer should be expected to get on our exam, right? Again, because we know what their score on the items are expected to be. So of course, we're going to have several judges at this meeting, 7 or 8, somewhere around there. And each judge for each domain is going to come up with this sum score, just as we just demonstrated here. And so we're going to have not just one of these, let's say that this is 5.77. Let's say that, judge 1, 5.77. But maybe judge 2 estimates that the cut score is like 5.6. And maybe judge 3 estimates that the cut score is 5.8, right? And you can see where this is going. But the point is that we will pool our estimates across judges, right? So, the easiest way to do that is to look at the average across judges, which in this case is 5.718 if we round. And we'll do more than one round, especially if we see heavy discrepancies. These are pretty close and nice. We might not always get that when we sit down to actually do the activity. But the point is that what we're going to do is have each judge look at each item using the software, as I've said. They're going to make those ratings for every item. That's going to get us an estimate of the total score from that judge. And then we're going to pool those estimates of the total cut score across judges to come up with the average cut score across judges. And once we've gone through a couple of rounds, and hopefully these things coalesce or come to agree at least relatively closely, that will become the cut score for that domain. That'll become our recommendation for the cut score for that domain. And then we'll move on to the next domain. And that's what we're going to set out to do. So just to give you a recap, we're going to keep these things in mind: minimally sufficient implementers, cut scores, false positives and false negatives. And we're also going to keep in mind these performance level descriptors, right? We're going to read these. We're going to use them to visualize the implementer who minimally meets these descriptions. And then we're going to use all of that information to estimate, for a given item, how well we think 100 minimally proficient implementers would score on that item, right? And once we do that for all of our items, we'll have our argument for where we believe the cut score should be. Once we finish that for all 3 domains, we're going to I'll take that information and I'll put it in my report, and that report will go to Carrie Sjogren, and Carrie will then take our information and use it to come up with the final cut score. She may just accept the cut score that we come up with at the meeting, but she may have other things to take into consideration, such as the number of teacher implementations that would be above or below the cut score and things like that. So, which reminds me of one other thing that I wanted to point out. So when we actually meet on the 30th, we're going to go through rounds, as I've just said. So after the first round of item ratings, say for adherence, just as an example, there's 3 items there that we'll rate. Once we've gone through and got our estimated cut scores for each judge, we'll look at how far away the different judges are, and we'll also look at some different information. So, I'll show everyone, where the judges are, how different they are, and I'll also show some information on the, I guess what we would call examinee distribution. So we can look and see how actual examinees scored on that item, just to sort of see, how realistic our estimates are. And then we'll do another round and have some discussions. And I'll also share some information about, how the estimate of the cut score would impact, historical implementers. That is, how many implementers, based on historical data would be above or below a certain cut score. And then we'll have more discussions, and then we'll do a final third round of ratings, and that'll be our recommendation for the particular domain that we're looking at. And that's it. That's what we're gonna do. If you haven't already, please look at the video or videos that were sent regarding the actual measure that Shada was kind enough to record. And please read the fidelity paper as well. And of course, review those performance level descriptors. So thanks for watching. Need to make sure that I stop recording.